Hello there, this is Kusal. Today we're going to be going over arrays and strings. But before that, let's go over what we expect in a coding interview. So they're going to be testing us on pretty much anything in computer science. It's going to be on a whiteboard or maybe even a code share, sometimes on a coding challenge actually. And they're really testing you on how fast you could come up with an efficient solution. You really need to be on your wits. The questions can be ranged from binary search trees to arrays to sorting, graphs, maps, stacks, etc. Pretty much anything. So we really got to be prepared. So a good starting point is arrays. They're one of the most important topics in programming and programming interviews in general. Most companies will ask an array question at some point in their interviewing process. And if they don't ask a directly array question, they'll ask you a string problem because those are pretty much just arrays, right? There's a lot of types of problems that we can expect. Properties of an array, 2D arrays, 3D arrays. One of my friends actually got a k-dimensional array question. Kind of absurd, but there you have it. Character arrays, strings, array lists, and sorting and searching will actually be covered in a separate lecture, but these are just general topics that we will see for arrays. Such an example problem is the following. Say we have a sorted array of positive and negative integers, and we need to find the pair of integers whose sum closest to 0. Our first thought may be, let's just check every single pair. So first, -7 and -4, they add up to -11. -7 and -2 add up to -9, a bit closer. -7, -1, -6, etc., etc., etc. And if we actually analyze this, we'd realize that we would get the right solution if we check every single pair, but we are checking every pair, which takes roughly n squared time. And additionally, we're actually not utilizing the fact that we have a sorted array to begin with, so maybe let's try to use that. Our solution is going to use 2 pointers. One is going to point at the very left at the beginning, the other is going to point at the very right. What we're going to do is we're going to add the values at these pointers, and see if we can do better by shifting these pointers around. So at the onset, we have -7 plus positive 10 adds up to 3, and we're going to store the current sum and the best sum in the top right, or obviously during our algorithm. This is a bit over 0, so maybe let's try decreasing that sum by reducing the right pointer and moving it leftwards. Now we have -7 plus 6, which adds up to -1, remarkably closer. It's only one distance away from 0, right? Now this is a bit too small from 0, so let's try to increment this sum by moving our left pointer forward towards the right? -4 plus 6 equals 2, a bit more, but kind of, you get the idea, right? We're moving the pointers inwards to try to get the best possible sum for any single value. So -4 plus 1 is the next iteration. That's going to add up to -3 below 0. So we're going to increment our pointer to -2 plus 1, which is going to tie with our current best of -7 plus 6 to become -1. Again, this solution is O of n. We're basically iterating through the array once. So yeah, that's our best solution that we can have. So a couple things that we can think about. So is this array already sorted, such as the previous solution? If it wasn't sorted, could we sort it? Would it still be the most efficient? And actually, just a tidbit about that. If we do sort it, we're limiting our solution to be at best n log n, because that's what most sorting algorithms run on. So if we can do better than n log n, don't sort it. If you can not do better than n log n, do sort it and see if it helps. What is the range of elements in the array? Sometimes the question will be from elements will be from 1 to n. Did I check my upper and lower bounds? Am I having any index out of bounds errors, etc., etc., etc. There's not a lot of edge cases that we need to test here, but a couple are empty arrays or maybe null arrays, arrays with few elements. So if our array only had one element, the pointer method actually failed. So yeah, repeated elements can sometimes be a bother. But in general, if we have any of these edge cases, all we want to do is ask our interviewer, what should we do in these edge cases, and handle them accordingly. You might think that with an array, there's really not much we can do aside from maybe iterating through it with a for loop. Actually, there's a lot we can do. So here are a couple techniques that we can use in our solutions. I'll go through each of them quite briefly. A sliding window is one of these really useful techniques. It's actually used in a lot of things, such as a rolling hash. Let's actually look at this problem. So given an array of size n and a number k, find the minimum summation of k elements. So in this example, we have a bunch of elements, and our k would be 5, right? We're looking at 5 continuous elements, and we need to find what the minimum sum is of those k continuous elements. So at the beginning, we're going to add these 5 elements from 8, 8, 5, negative 5, 8, 8, 5, 9, and 3. See, the sum is 33. When we want to find the next sum, we're just going to add the 2 and subtract the 8 from the beginning, right? And we're going to get the sum of 27. Next, we're going to add 3, which is our next element, and then subtract this 8, and it's going to be 22. We could continue this onwards until we reach the end of the array, at which point we'll have our maximum sum. This definitely beats kind of figuring out the sum individually without looking at the previous step. Another technique that we could use is called fasti/slowj, which is also so useful in various algorithms such as quicksort and partition in general. What we basically want to do is have 2 pointers, one moving kind of fast, which really searches for things, and one moving slowly, which kind of keeps a stationary point. So in this example, we're going to be trying to move all the 0 elements to the end of the array. Our fast green pointer, or the fast I, is going to point to non-zero items, and it's going to be searching for these non-zero items to put at the beginning of the array. Our red pointer is going to point at 0 items, or just point at kind of the location where the next non-zero element should go. So at the beginning, they kind of point at the beginning, at the left side of the array. The green pointer points to something non-zero, so it's going to swap. Next, the green pointer is going to look for something that's non-zero, so it's going to find this 3, and then it's going to swap again with the orange pointer. The orange pointer is going to increment, so here it goes. The green pointer is going to look for another non-zero element, and then swap again, at which point we're done because the green pointer is at the end of the array. Finally, another trick that we could use is using the array as kind of an index array, almost like a map or a set. So say, for example, we have this array of elements 7, 3, 8, 1, 2, 5, and we want to see what's in this array. We could create another array with indices from 1 to 8, and kind of use each value as a flag of does this element appear in this. This is actually useful again in various modern algorithms like counting sort, bucket sort, etc., etc. Let's move on to strings. And for this, I'm not going to go over too many techniques, so more as some problems. So our first problem is going to be valid parentheses. Note, I urge you to pause the video and try to solve the problem by yourself before I actually go over the solution right after. Would be really good practice, but I don't know, your choice. So here's the question. Given a string containing just the characters of open and close parentheses, open and close curly braces, and open and close brackets, determine if the input string is valid. And you can kind of intuit what this valid string would be, right? When you open a parentheses, you need to close that parentheses, but you don't want to close it too soon or too late. Let's go over some examples. So obviously this is fine. We're opening and closing a parentheses. This is fine. We're opening and closing them kind of one after the other. But for example, this one is not fine, right? We're closing and opening this one, but it's in the wrong order. Yeah. So say this is the input for our question. What we're going to do is use a stack to solve our problem. Just a reminder, a stack is kind of like a queue, except for its last in is first out. Kind of like a pile of plates, actually. The thing that's on the top gets taken off first, but that was the one that was put on most recently, right? What we're going to do is when we see something that opens a pair, so opening parentheses, opening curly brace, or opening bracket, we're going to put it on the stack. Once we see something that closes a pair, we're going to take off the top of the stack, so pop off the stack, and make sure that that's the proper pair. Hopefully this makes more sense once we go through this example. So we're going to see that the first character is a opening parentheses, so there it goes on the stack. So is the second, it's a opening curly brace. Top of the stack it goes. Oops. The next character is a closing parentheses, right? Or sorry, closing brace. Now we're going to pop off the top of the stack and make sure that these are a proper pair. So this went over there, and this came over here, right? And yes, that is a proper pair. It's a closing brace associated with a opening brace, and they're both curly, right? We're going to keep on going now. So top of the string gets removed. It's a opening brace, so we put it on top of the stack. Closing brace is next, so we pop off the stack, and then compare it with the thing that is in our string. And again, this is a proper pair. Gucci again. Finally, we're going to go back to our string, look at the last character, see that it's a closing parentheses, and we're going to pop off the top of the stack, and this one and these ones are already gone, so it's just this one. So we have an opening parentheses here, and then a closing parentheses here. And again, that works. Since our stack is empty at the end of the day, this is a proper input string. In our next example, we're going to go over something that's a bit... In our next example, we're going to go over something that's incorrect. And you can kind of see that this isn't correct. It doesn't really close everything it opens. But let's use our algorithms to actually prove that. So we're going to take the first character, it's open. Take the second character, it's also an open. And then look at the last character, it's close. So we're going to pop off this stack right here. This close goes right here. That's good. So we keep on going. But wait. We've ran out of characters. And we still have something in our stack. Because of this, this couldn't have possibly been a good input string because we still have stuff that we need to close. Therefore, it is false. Another technique that we can use is a kind of using that array as a hash map. This kind of goes back to using an array as like an indices map. But specifically for strings, we can create integer arrays from 0 to 25 to represent the characters from A to Z, or maybe 0 to 127 or 0 to 255 for some of the ASCII tables. And here's a question that actually really abuses that. So say we want to find pangrams, and a pangram is basically a sentence or a set of characters that have every letter in the alphabet, right? All 26 of them. And such a pangram would be the quick brown fox jumps over the lazy dog. There's A, there's a B, C somewhere over here. Yeah, C is right there. D, etc., right? In general, the question is, if we have any string, check if it's a pangram or not. So say we have the phrase cab bed, and we need to figure out, is it a pangram or not? And obviously, this only has 6 characters, so it couldn't possibly be containing all 26 characters. But in any case, let's try to figure out an algorithm for really any string to check if it's a pangram. What we're going to do is we're going to use what we saw on the previous slide and create kind of an array that stores these characters. So this array is going to be specially made just for this problem. It's going to have 26 spots, kind of dot rest. So here are the indices for, and it should end on 25, right? 0 indexed. But even though the indices are obviously numbers, what we're going to think about the indices are the letters themselves, right? A, B, C, D, E, all the way to Z. And we're just going to go through this string, and whenever we see a character, we're going to check it off in this array. So C is going to be checked off right here. This A is going to be checked off right here. B again, but we've already checked it off, doesn't really matter. E, and then finally D, right? And yes, we've gotten all the characters from A through E, but if we checked for F, it's not going to be here. We can kind of think of this array as like a Boolean array, right? Where everything was originally set as X's, and once we see a character, we're going to set it to true. Using this algorithm, we're going to go through our string once, and then we're going to finally go through our array at the end of the day once to make sure each of the boxes are checked off. This is going to run in linear time, and really is the best we could hope for, because obviously we need to look at the whole string. What you could think about what we're doing here is we're kind of treating this array like a set, right? We're keeping track of what's in our string using this array. The benefit of this is that we're using an array, not a set. An array has much less stuff to deal with, and array is just a simpler data structure. It will really wow your interviewer. So there's the end of our video. I hope you guys learned a lot. See you next class.